All right, so chapter 2, big picture day is what I'm going to chat about today primarily, and then we'll start into 2.1. It's all about limits. And so in pre-calculus, you talked about end behavior some. Whoa, look at this guy. Whoa. And so if this is f of x, we said the limit of f of x as x approaches infinity is 0 because it approaches 0. The y's get closer to 0. And we're like, yeah, okay. You did that. And you also did, whoa. And here is x equals -6. And so as you approach -6, the limit as x approaches -6 of f of x is, well, now hold on, bro. Which way did you approach it from? So that's something that we didn't talk about in pre-calculus. So we're going to define this as we approach it from the right. We put a little plus sign there. As we approach it from the right, this is going to -infinity. And as we approach it from the left, as x approaches -6 from the left, that is from the left, from the negative side, it approaches positive infinity. Okay? And think about the things that can happen. Either functions can either go to positive infinity or negative infinity, obviously. Or they could go to a constant. They can go to 0, they can go to 1, they can go whatever. You know, in pre-cal, we looked at functions like this guy, 3x plus 2 over 2x minus 7. Hey, what is the limit as x approaches infinity? Well, the top becomes 3. Let's let x equal 1 billion. 1, 2, 3, 4, 5, 6, 7, 8, 9. As x approaches a billion, the top basically becomes 3 billion. But Greenwood's 3 billion and 2. Yeah, it's 3 billion. Nobody cares about $2. Over 199,999,993. It's 2 billion, crackhead. Wait, is the top bigger? Yes, the top is 1.5 times bigger. And so what we would say is the limit as x approaches infinity is 1.5. In other words, the top will always be 1.5 times bigger than the bottom in this case. Or in other words, it's going toward some constant. What if it was this? Well, then it'd be a 3 to 1, yes? Okay, piece of cake. Now, what if it was some other? Now, by the way, some of these are just obvious, right? You're like, what if it was x cubed minus 7x plus 5 over x plus 1? Hey, here's the limit as x approaches infinity. Well, the top is getting huge, redonkulously fast. In other words, it's really just x cubed over really just x, which is really just x squared. In other words, as time goes on, as I get over this direction, I should be expecting it to go up and act like a parabola. That is, I should expect it to be going to infinity. Right? Right? And ditto, going the other direction. It's also going to finish up the other way. How do you know, Groom? Well, I know because x cubed, again, divided by x. So let's say x was -1 million. Whatever, cubed. Is still negative. Over -1 million is really just -1. Negative 1 million, whatever, squared when it's done, right? Which is still negative. Yes? That's the idea there, okay? I'm sorry, positive. Sorry, they cancel out because the positive cancels. That's what I'm going to say. So in other words, it's going up. So over here somewhere, it's going up as well. But what happens at -1, Groom? Whoa! That's an asymptote. An asymptote. Say it with me now. Tote. Okay? So when you do this, well, Groom, what are you going to do? Well, I need a value on the positive side. Now, what would you choose? Well, let's get a number that's close to it. You go, what about 0? Okay, what about 0? At 0, you put 0 into there, you're going to get 0 plus 5 divided by 1, so 5. Now, if I'm a betting man, I bet it's doing this number, like so. And I bet over here it's going to come back up because we know it has to come up this direction, yes? We'll look at the graph momentarily. If you don't believe me, we'll plug in -1/2. -1/2 cubed is -1/8. And -1/2 times 7 is positive 3.5. Plus 5 is, well, it's up here some more, bro. So we were clearly going to infinity, right? On this side, my guess is it's going to be either doing this number like so, or it's going to be doing this number like so, yes? Now, again, we set it -1. Well, what about -2? What about it, sir? -2 cubed is -8 plus 14 plus 5 over -1. All right? So that's going to be 19 minus 1 is 11 divided by -1 is -11. Judas Priest, I bet it's doing this number. Yes? And you can see that from the graph. We will be, of course, using Desmos for some of this, but we're going to be doing a lot. Let me repeat that. A lot. Doing it the right way, which is algebraically, because I need to get you doing things at a high level so that you are comfortable when it comes to calculus. If you think you're going to go to college and be an engineer and whatnot, which is great, I think you should, some of you should probably, then you need to get a lot better at your algebra. Some of you are not great at your algebra. Dude, it's like I know what I'm talking about. How weird is that, huh? That's hot. So we'll be doing a lot of those. We're going back and assessing stuff we already know. Some of them are obvious. And then we're going to get some really funky ones, like this guy, for instance. What if you take x plus 1 divided by the absolute value of x plus 1? What does this guy look like? Okay. Well, obviously at -1 it changes sign, yes? At -1 it becomes 0 over 0. So at -1 we got a problem, obviously. And you're like, well, what kind of a problem is it? Is it truly an asymptote? Well, not really, because this guy and this guy kind of cancel out, right? Right? It's 1-to-1, but not so fast, Haas, because that bottom guy is always positive. Always positive. The top guy is positive as long as x is greater than 1. So this is 1, kind of. So it turns out that from here over, it's 1. And from here over this way, it's -1. What happens there? Nothing. It doesn't exist there. Is it an asymptote? No, just a hole. Well, which position does it take on? Well, it can't be -1, bro. So the limit as x approaches -1 of f of x, well, first of all, does not exist. Notice that the limit does not exist. Now, we say the right-hand limit, that is the limit as x approaches -1 from the right, that totally exists, and it's 1. We say the left-hand limit, which is the limit as x approaches -1 from the left, is -1, and it totally exists. But if the right-hand limit and the left-hand limit don't match up, then the limit does not exist. That's a big deal. That is a huge concept. Like, really big. Like, wow concept going forward. Okay, because that's a big deal. Everything we do in calculus relies on a thing called continuity. That is that there's no gaps, no holes, no jumps, no whatever in my function. That is, over the interval in question, my function can be drawn, if you will, without lifting your pencil. And that's a big deal. And part of continuity is the idea that, well, the right-hand limit and the left-hand limit are the same, and they're the same, and therefore the limit exists. That's a big deal. We'll talk more about that later on. Okay. Now, for many functions, that's true. For instance, this guy. Hey, what is the limit as x approaches 3, Groom? Why it's 3? Weird. Whoa. What is the left-hand limit? Well, the limit as x approaches 3 from the right of f of x is equal to the limit as x approaches 3 from the left, which means the limit is 3, right? That is, what is the y value? What is it approaching? Okay, that's a huge concept, and as you can imagine, there are some problems like asymptotes. Anytime you have a vertical asymptote, we lack continuity. You with me? I cannot draw that because it can't go all the way to infinity. That's a problem. We've seen some other ones where you're just going along and all of a sudden, boop, jumps up to here. Yes? Oops, I did that backwards. Boop. Perhaps, darn it, you jackass. Excuse me. And so up until your birthday, you are 15 years old. On your birthday, bam, you're 16. Well, I was 15 and a half. No, you're 15. Now you're 16. Okay, whatever. Hey, Mr. Groom. If you park in our parking complex for an hour or less, it's this much. As soon as it's over an hour, boom, it's this much. You with me? But it was an hour and 1.000 seconds. Yeah, what part of over an hour do you not grasp, dude? It bounces up, okay? In either case, there's a jump, and we say that it's a discontinuity there, okay? We'll see some others. This one, for instance, the x-axis does not curve uphill last I checked. Boop. Mr. Groom, this is the square root of x, is it not? Well, good job. Way to go, Nathan. I appreciate you noticing that. It is the square root of x. What happened at 0? It was going along, nothing happened. There was nothing. All of a sudden, bam! There's 0. Let me tell you, kids, 0 is a lot different than not being a thing at all right? Like, how many tacos are there? This is a lot different than, what the hell is a taco? You with me? Tacos have not been invented. So, huh? Or I didn't have any tacos today. You with me? How horrible of a world would that be if tacos had not been invented? Do you know what I'm saying? That'd be terrible. Versus, I know they're there. I just didn't have any today. Okay? That's a big deal. This function is not continuous at 0, technically, because the left-hand limit does not exist. You cannot be on the left-hand side of that guy. And so what we'll talk about a little bit more later on is that, are we gooch as long as we're not on 0? Yeah, or all the way to 0, as a matter of fact. We're good in terms of the actual function. But if you think about that, we would say this one actually has its right-hand continuity. Okay, is right continuity. It is from the right. As you approach 0 from the right, we're gooch. It's only at 0 there's a problem. Now, that's going to be a big deal later on. Okay, because later on we're going to start in chapter 2. We're going to discuss, well, how fast is it changing? Well, right here, it's pretty obvious. We can get a rate of change, kind of a slope kind of a thing, if you will. That makes sense. But what about at 0? Well, it didn't exist, and now, boom, it's at 0. Well, how fast did it do that? Instantaneously. That sounds like an asymptote. That's correct. That is correct. Because if you think about this, slope is a rise over a run. Oops, rise over run. Right? Which is a change in y over a change in x. If x is time, and if something changes in 0 time, I just divided by 0. And when that happens, what do I get? I get an asymptote. And so the rate of change would have been infinite at that point, yes? Because there was nothing, it didn't exist, and now there's just, there's nothing, but there is none. But none is a lot different than doesn't exist. Okay, it's kind of weird that way. Not to get too esoteric on us, but that's kind of a different thing. Okay, and so then we're going to be talking about that. We're going to be doing a lot of simplification going forward. And so you might remember this from pre-cal. And so x squared minus 6x minus 7 over x plus 1. And you're like, Groom, you remember this back to pre-calculus. You factor the numerator, minus 7x plus 1. Remember doing that back in the day? And maybe you remember this, cancel. And remember saying something like, there's a hole at x equals negative 1. All right, remember doing that? But you're saying that this equation is the same as x minus 7. Well, x minus 7 is 1, 2, 3, 4, 5, 6, 7. This is x plus 7. This guy is the same as it, except at negative 1, there's a hole. Are you with me? There's a hole. How do I know there was a hole? This is like getting dumped by your high school girlfriend. There's a little hole in my heart. Oh, I'm over it. Found a new girl. Ha! All right, but there's a little hole right there. I filled it. I got rid of the hole, if you will, yes? It canceled out. If it cancels out top and bottom, it's a hole. If it stays on the bottom, if when we were done we had an x plus 2 in the bottom, we'd have an asymptote at negative 2. But in this case, it canceled out, so we have what's called a hole. And so if I asked you, hey, what is the limit of x squared minus 6x minus 7 over x plus 1 as x approaches negative 1, for God's sakes, most of you go, oh, it's 0 over 0. Oh, it's undefined, Mr. Groom. Those people will be exposed to ridicule. The people who do it right will go, Groom, I simplified it to x plus 7. That's right. Good job. So the limit as x approaches -1 is simply, if you plug -1 in there, you're going to get 6. That's x minus 7, dumbass. Try again. X minus 7. So the limit is -8. Attaboy. Yay! That is true. That is the value that would fill it in. Okay. And again, if you look at that on the graph, parentheses x square minus 7x minus 6. No, that's not right. Divide by x plus 1. Hey, it's a straight line. That's hot. It's a straight line everywhere except there. As I trace this direction, coming that direction, it sure looks like it's going to get to -8 and then nothing. If I'm coming this way, it sure looks like it's going to get over here towards... Come on, you hippie. Come on. Freaking pig. Sure looks like it's going to get closer and closer and closer to -8, and then it just doesn't. And so the limit there, we'll be doing a lot of simplification on these guys. Now, there'll be some where their limit does not exist. For instance, the sine of x. The sine of x. What is the limit as x approaches infinita of sine x? You're going, yo, no say. I don't know either. I don't know. And here's how I know. Because sine does this number. Forever. And so where's infinity? I don't know, bro. Here's what I do know. It's going to bounce back and forth between positive and -1. There'll be some, and we just won't have a limit for it. Okay. I will say once in a while, I like to say that this guy has a limit as x approaches 3 here, or whatever. That the limit is infinity. Some books, I think including yours, say there is no limit. I don't like that because no limit is this idea it bounces forever. There's no limit. That's true. I understand what they're saying with infinity. Infinity is not a thing. It's not a number, so therefore there's no limit. I don't like it. So I like to say infinity. Positive infinity or negative infinity. Which way is it going? That's what I want to know. Okay? So that's that. Now, in 2.1, we're going to introduce this concept for the first time. It's not the only time we'll do it. Not even close, bud. Here is y equals x squared. If I wanted the rate of change here at 1, what could I do? Okay, well, guy could go, well, I could pick a point over here, like, I don't know, 1.05. And I could graph this line. But notice that this line will actually cut through the graph. Okay, but I could find the slope is equal to 1.05 squared minus 1 squared over 1.05 minus 1. Right? That's true. Remember, that is f of x plus h minus f of x over x plus h minus x. H being the distance between them, which in our case is 0.05. And so this then simplifies just to this guy. We will be looking at this a lot. A lot. And so we're going to get 1.05 square minus 1 is that divided by 0.05. And so we're going to get about 2.05. 2.05 is the rate of change when we're at 2. And you're like, but Groom, couldn't we get a little closer with our, couldn't we make our h a little smaller? You're right, we could. What if we do 1.25, or 1.025, sorry. 1.025 squared minus 1 squared over 0.025. It's a great question on your part. Love you for asking it. It's a good deal. 1.025 square divided by 0.025 is, Mr. Groom made a boo-boo. Oh, sorry, my bad. Minus 1, dummy. And lo and behold, it's about 2. That's weird, 2.025. In fact, we're going to be taking the limit of this thing as h goes to 0. That right there is the definition of what's called a derivative. Now in section 1, you're going to be doing an approximation of this, going, hey, let's do this. Let's find this slope at 1. Okay, cool. And then we'll use these various scenarios. So like 1.0, 1.1, 1.05, 1.025, 1.001, et cetera, et cetera, et cetera, right? This is your x's. These are your x squareds, right? And we'll plug them in, then we can find these, and we can actually find the rate of change. And what we shall see is, as the h gets smaller, this comes closer and closer and closer to being what we call a tangent line. As of right now, that's a secant line. That is, it's cutting through the graph like so. But as h gets closer and closer to 0, those points become the same point. Now there's a problem with that. How many points do you have to find a straight line? I'm sorry, the equation of a line. We need 2 points. But if you're letting h go to 0, you're saying, well, we're not going to have 2 points. Well, at that point, it can't exist. Wait a minute. That's the very definition of a limit, Groom. That's right. And on top of that, my man, it should also work on the other side of 1. Well, what do you mean? Well, I mean like 0.99. Well, that's a difference of 0.01. I know. So 0.99 square minus 1 square over 0.99 minus 1. So that's going to be, check it out, negative on top, 0.99 squared minus 1. You friggin' hippie. You worthless freeloading bum. Divided by 0.01. Shut your mouth. It's about, divided by negative 1. My bad. Hold on, let's try it again. Divided by negative 0.01. It's almost 2 again. That's right. And what we'll see is that this slope that we just found, the slope will be the same regardless of which way we come at it. And that's a big deal for most functions, okay? Now, there'll be some functions where that won't be true for. For some functions, there's going to be a problem, okay? So, like, for instance, this function we did earlier, where it was down here and then all of a sudden it bumped up to here or whatever. Hey, what's the slope down here? Well, it's a bad example. The slope down here was 0. Slope up here is also 0. It's just weird. Let me get you a different one. So this one maybe. And then, hey, the slope down here was, let's say, 1. Slope up here is a half. It matters. In other words, it won't always be that where it's 2. But most of the time that's the stuff that we'll do. And so it has to do with, hey, let's take the limit as we do these guys, okay? So your assignment I'll have posted online. That'll get you started. That's 2.1 and kind of a big picture day for the chapter.